Before utility wires traced across the sky, night was ruled entirely by fire. If you wanted to push back the dark, you had to ignite something: whale oil, tallow candles, or municipal gas lines, meaning every light source was an open, dangerous flame. Electricity offered an alternative, but it brought its own logistical challenge. Unlike coal or oil, electricity cannot be harvested or mined, and it cannot be stored in large quantities. It is a form of energy that must be manufactured, generated precisely at the moment of demand. The first successful proof of concept for this real-time manufacturing arrived in September 1882. Thomas Edison and his associates powered up the Pearl Street Station in New York City, using steam engines to spin generators and send a steady electric current to incandescent lamps in the surrounding neighborhood. Generating that current required massive amounts of coal and complex machinery. Pearl Street proved you could deliver invisible power over copper wires, but the difficulty of manufacturing it meant electric light remained an isolated luxury, trapped within a single square mile of Wall Street. The system Edison used was built on direct current, or DC. In a DC system, electrons flow in a single, continuous direction. It worked for powering small, dense areas, but it had a severe engineering flaw: massive transmission inefficiency. The further the current traveled down the wire, the more power it lost. This schematic illustrates the physical constraint of early power grids. A direct current plant could only push usable electricity outward in roughly a 1-mile radius before the voltage dropped too low to power a lamp. Beyond that strict boundary, the wires went dead. Because of this limit, you couldn't build one large power plant for a whole region. You had to construct a new steam engine and generator for every single square mile. The infrastructure costs were staggering, meaning only the wealthiest, most densely populated urban centers could afford it. Dictated by the physics of direct current, electricity could never function as a global utility. Without a way to push power over long distances, the vast majority of the world was destined to remain in the dark. To overcome these infrastructure costs, early electrical manufacturers developed the central station strategy. Instead of selling small private generators to individual buildings, they realized they could spread the capital costs across a wider network of local users by operating a single shared power plant. Driving this expansion required immense scale. Companies like the Thomson-Houston Electric Company aggressively organized these local utility stations. Their sales managers traveled from city to city, helping local businesses secure capital and obtain municipal franchises to build generation plants block by block. The first visible public result of this rollout was the carbon arc light. These systems sent electricity jumping across a gap between two carbon terminals, creating a brilliant, intense light perfectly suited for illuminating factory floors and public street lamps. While central stations and bright arc lights conquered the commercial districts, the physical limitation of copper wires remained. Direct current still couldn't push power far enough to reach the sprawling residential neighborhoods located miles from the downtown generators. Expanding the grid to ordinary homes and distant towns demanded a shift in physics. The industry had to move past direct current and manipulate alternating waves to carry power across the open landscape. The breakthrough that solved the distance problem was alternating current, or AC. Instead of flowing steadily in one direction, alternating current reverses its direction at regular, rapid intervals. The Serbian-born American engineer Nikola Tesla discovered the core principles and patented the motors that allowed AC to generate and transmit large blocks of power. This line graph shows the technological logic that made AC so powerful. Alternating current allows the voltage, the pressure forcing the electrons to move, to be stepped up to massive levels. This high-pressure current travels efficiently over long distances with minimal power loss, and is then stepped back down at its destination. The ultimate proof of this capability arrived in August 1895. Water flowing through turbines at Niagara Falls spun massive AC generators, and that power was successfully transmitted a full 20 miles away to the city of Buffalo to run streetcars and municipal lighting. By decoupling the power plant from the light bulb, alternating current untethered the electrical grid. Generation plants could be built near cheap fuel sources or distant waterfalls, while the power itself marched out of the dense city centers and across the open landscape. Transmitting power efficiently over long distances created a terrifying new problem. It meant bringing deadly 1,000-volt transmission lines directly to the wooden walls of domestic family homes. Before this system could be commercialized for private use, inventors like Elihu Thomson had to domesticate the power. They engaged in intense engineering struggles to invent quiet, unseen safety mechanisms, like secondary ground connections and short-circuit fuses, to minimize the danger of electrocution and fire. They relied on heavy transformers mounted on street poles to strip the lethal 1,000-volt transmission current down to a gentle, survivable 110 volts just inches before the wire crossed the property line. The final obstacle to a fully electrified world was safety. Before electricity could enter a private residence, engineers devised quiet and visible safeguards, allowing families to live inches away from a lethal manufactured force. The physical connection of the grid to the individual consumer was finalized with the installation of the kilowatt-hour meter. It stood at the edge of the home, carefully measuring the exact amount of manufactured product the resident pulled from the line. Slipping a switch represents a quiet, life-altering shift for the homeowner, the instant replacement of an open flame with the steady glow of an incandescent bulb. What started as a strict 1-mile radius in New York City eventually expanded into a massive, interconnected physical infrastructure, stretching endlessly across fields to supply small towns and rural homes. The electrical grid exists as a meticulously constructed physical web, a network financed block by block and built pole by pole that permanently pushed back the darkness.